Hello friends, today just we're going to start the topic called application of transport phenomena as a continuation to the last unit that I have done for in case of thermal conductivity, the viscosity and the momentum transfer that we have discussed in last class. So over here we are seeing the basic equation from the transport phenomena. So this F is given by, this is the whole of the transport phenomena that is being borrowed from the basic deduction of transport phenomenon. So here we are just going to discuss something about a physical quantity called diffusion. So what happens in a diffusion? Suppose this is your reference plane. From here P1 and suppose here P2. The gases at the lower level has higher concentration and the gas at the higher level has, here it is high concentration and here concentration of low. So diffusion is a process through which we know the molecules from the higher concentration would move to the place of lower concentration. So the value of P1 would be P1 is equals to N plus dH by dz into r cos theta as per spherical polar coordinates, and P2 is equals to n minus dH by dz r cos theta. So using this total stuff, and here the transfer is the molecule is being transferred from one point to another. So obviously if we wanted to find the difference of del F, so here the difference of del P2, del P would be there, that is P1 minus P2, which would mean 2 into dH by dz into r cos theta. Okay, so here the H is the elementary number of particles which are having the velocity range between C and C plus dc. So from Maxwell distribution we know that it is equals to 4 pi n aq e to the power minus bc square c square dc. This is what we know. So applying this as dH by dz, we have 4 pi aq e to the power minus bc square c square dc into dn by dz. So we are going to use dH by dz. In place of dH by dz, we are going to use this. So using in the above equation, so we replace the dH by dz by this quantity and we will modify the equation. So we have del F is equals to dA by dt by 2 pi into 4 pi aq e to the power minus bc square. Then we have c square dc will become cq dc, and the velocity would run from 0 to infinity. And then we have 0 to pi by 2 cos square theta sin theta d theta integration 0 to pi d phi, and the remaining is there. Integration 0 to infinity r r by lambda. So this evaluates to AQ dt dn by dz. I missed the term dn by dz, it should be here. dn by dz should be there. dn by dz. Then you have 1 by v square. This integration will lead to 1 by v square. That should be 2v square into gamma 2 into 1 by 3 gamma lambda gamma. So this is the expression for del f, or rather you can call it this also as del f, for the expression that we obtain in case of diffusion. So remove this term now. Now the net expression will be like this. The net expression is and here we have AQ by 2b square would lead us to root over 8 AQ by x. So now equating del f we have with dq is equals to capital D, the diffusion coefficient, into A into dn by dz into dt. If we equate these two terms, then this dA parts get singled out and dt gets singled out, dn by dz gets singled out. So we have the diffusion coefficient can be written as coefficient can be written as by using dq is equals to del A. We get this. We are singling out and we are getting capital D is equals to 1 per lambda where C equals to root over kt by m. This is what we get. This is the velocity of c as obtained from Maxwell distribution. So we get this. So now we can write. We know viscosity is equals to 1/3 mn c bar lambda. If mn is replaced by rho, which equals to density, then theta equals to 1/3 rho c lambda. Now if we equate, this is suppose equation A and this is suppose equation B, what we get, A divided by B is equals to d by theta. Mother got cancels, this gets singled out, this gets singled out, this C gets singled out, this also gets singled out. So eta will be left with so the important relation that we get over here is eta is equals to rho times diffusion coefficient. That's all. Thank you.